Today, we will discuss one more methodology called multi-cycle approach to design the process. And so what is the objective of this design? So we want to design a processor whose clock period is T should be lesser than the single cycle based approach or single cycle processor that we have discussed in the previous classes. So that is the primary objective, and we have also other secondary objective like we'll see in that in the successive lectures that we are using, many more resources for single cycle approach. Okay, like we have used, more than one adders, also more than one memory when we designed a single cycle processor. Okay, and also like here, in single cycle approach. Okay, so each instruction is taking same amount of time that LW is taking. Because why? Because you see, if you remember the clock period calculation, that is T. So that we have calculated by using the source and destination pair. And if we remember that LW source and destination pair was mode. Okay, and that dominates the clock period. And because of that, every instruction in single cycle processor taking the same amount of time. Okay, so like there are few instructions which can take less amount of time, like such as R-type instruction, right? So unnecessarily they are waiting for extra amount of time to finish, right? So in that way, single cycle based processor is not taking care of the other instructions execution time, right? So here we want to uh, give focus on that part. So that we are saying that common case analysis, meaning that here each instruction will take same exact amount of time to finish its execution. Okay. So what are the objectives then? So primary objective is to minimize the clock period. Okay. And besides that, we have secondary objective, right? We want to minimize the resource utilization. Okay, and also we'll take care about each individual cases. So cases means like each instructions, right? And we'll give exact same amount of time to each instruction to finish its execution. Okay, so these three are the objectives. Okay, so if you remember, so this table we saw when we designed the single cycle based process, right? So, and we have already, let's say you can consider this way, these components are already designed and they are available in a as a library form. Okay, like meaning that we have a library and where we have kept these modules. Okay, so here you can see memory read is taking 250 picosecond, register read is taking 150 picosecond, however register write is taking 100 picosecond. So in this way we have this component, right? We have already seen, and to design such component we have used this 65 nanometer technology. Okay, so if you remember, so this is the data path for the single cycle processing, right? So here you can see, so this is the PC. So first what we'll do, so we'll fetch the instruction, right? And through this memory, this is the instruction memory, and we will provide the address using PC, right? And then instruction will be available here, right? And then we'll read, or decoding will happen. We'll read the value from the register file, right? Got it. And then you can see we'll perform the operation using this ALU, and then we'll store, or we can read the value from the this data register, and then they are coming. The register is, I mean, the output from this memory, they are coming out, and then we are writing it back to the this register file. So if you remember the LW's data path, right? So LW, like, it will come via this path. I mean, first we have to provide the LW's address, right? So address will come via this, and then we'll read the LW here, right? And then we'll perform the effective address calculation using this ALU, and then this address would come to the data memory, right? And then we'll read the value from the this data memory, and then value would be available here, and using these marks, right? So this value would be come back to the register file, right? And then we'll write the value, and the address will come via this path, right? You remember? So in that way, you see, this is the source, right? From here, we are getting the address of the LW and this register file, right? This is the register file. So this is the destination. Got it? So you see, this is the longest path, right? Got it? And then, right? So if you remember the delay calculation, so this is source and this is destination. So this is the longest path, and this is dominating in the single cycle based processing, right? And this path decides the clock period. Got it? And so in that way, we have seen this formula, right? So this clock period calculation formula that we have just discussed, right? And here in single cycle based processor, the CPI is 1. Right? So CPI means a clock per instruction. Each instruction is taking 1 clock cycle. Okay, and that clock cycle, I mean the period of clock cycle, is dominated by the slowest instruction. Okay, and here LW is the slowest instruction. Okay, in the MIPS architecture, right? Got it. So now we want to improve this clock period. So that is the primary objective. Okay, and we have seen this formula also earlier. So here, as we are discussing about the general purpose processor, and here we want to execute the program, and program is nothing but set of instructions. So you can see this formula. So we want to find out the execution time of a program, right? And program has set of instructions, and then each instruction is taking the cycle. So that is cycle per instruction, and then this is the T, actual time. Okay, so this is the T. Okay, so we want to minimize this T. Okay, so that is the goal. Okay, and here, I mean, we are not, I mean, here you can see the number of instruction of a program is, I mean, it's a fixed, right? Because if we compile the program, then we'll have the set of instructions, right? And we are not touching that part. Okay. So one can, if one can interested, so they can go for compiler optimization, then number of instruction can reduce. Now, right now here question is, how did we measure the clock period? If you remember clock period calculation, also we just saw, right? So for each, so if you remember, so we have to find out source and destination, right? So here PC is the source and the destination here is the register file for LW, right? Similarly, if you remember SW, right? SW, so PC is source and this data memory is the destination. Got it? So in this way, we have to calculate the source and destination pair, source and destination pair registers, and then we have to find out the maximum one, and that will decide the clock period. So, got it? So here you can see. Okay, so here you can see. So this is here we want to minimize the clock period, right? And so now here you can see, so like for single cycle data path, right? If you remember, so we have this like also if you remember, the timing calculation, right? So we measure the timing based on these two D flip-flop, right? If you remember. And here, so for our single cycle data path, this D flip-flop is nothing but our PC, right? Got it. And then, right, we have the combinational logic. We are performing the execution of the instruction, and then we are storing that output or the result produced by that instruction, right? So this is the destination. So for here in our single cycle approach, so this D flip flop can be like for SW it can be memory, right? For data memory. For LW it can be register file. Right? For archive instruction it can be also register file, right? Got it. And all for also like for when we are calculating the PC plus 4, right? Then the PC itself is a source and also PC itself is a destination, right? So if you remember, got it. So here, if the period of this clock is T, then the frequency will be 1 over T. Right? So now we want to reduce this time, okay? Or we want to reduce the T. So how can we reduce the T? So we can partition this entire combination logic into smaller part. So here you can see we have partitioned this entire logic into two parts. Okay, you can see the combination logic 1 and combination logic 2, and the entire combination logic is nothing but the union of logic 1 and union of logic 2. Got it? Now here, okay. So here you can see we have the D flip flop here and here, right? So what we'll do? So first we'll take the input here, okay, and then you can see we'll log this D flip flop, okay. So we'll first take the input and then we'll log it, okay, and then we'll supply that input to this combination logic and then we'll perform the operation. Okay. After performing the operation, we'll store the result in this flip flop, and because of that, we have to open this gate. So it is nothing but our enable input. Okay, right? We are opening the enable input here. Okay, but remember this is also enable input, but we are not opening it, meaning that we are not allowing any instruction or any data to come inside. Okay, so this is locked. Here we are enabling the this D flip flop, and then output would be stored here. And then in the next cycle, so that output would come here. Okay, it will perform its operation here through this combination logic, and then we store the data here. Okay, and because of that, we have to on the enable of this D flip flop. Okay, you see, we are enabling the input here. We are enabling the D flip flops input here. Got it? Then data would be stored here. Now this time, right, we'll open this enable. Okay, and then next data would come. Got it? So then we'll get the then we'll get the output here, and we'll get the next input here. Got it? So this is not the pipeline only. Okay, got it? Why? Because in the pipeline there would be continuous flow of this input, but here you can see we are enabling this input, okay, at the beginning, right? And then we are performing the operation, and then we are enabling this input the next clock cycle, and we are holding the data here, and then that data is coming out through this flip flop, and we are performing the operation, and then, right, we are storing the data, and because of that we are enabling this one. But in this case, when we are enabling this one, this enable is 0. Okay, and same time we are enabling this one. Got it? So in this way, the data would, or input would come from this first stage. The input would go via this first stage, and then the second stage. Okay. So in that way, you see, if we split this entire combination logic very balanced way, then you can see the T would be reduced. Why? Because if you remember the timing calculation, so we have to find the timing between this one, and then this one and this one. Because in this case, this would be source and this is destination. And in the next cycle, it would be source and it would be the destination. Got it? So in that way, right? If you remember, so this is the source and destination, right? And another source and destination here. Then we have to take the maximum. Got it? So in this way, we can reduce the clock period. Got it? So same thing that we have discussed, like when we discuss about the LW, right? Because in single cycle data path, LW dominates the clock period, right? So we want to split the LW's data, right? Data path into smaller part that we will see. Okay, got it. So for LW in this case, if you remember, this is the PC, and in this case, this was the your register file. Okay, the destination. Okay, so the so the goal, I mean, if we want to reduce the clock period, right? What we have to do? We have to insert the register in between. Okay, and also we have to partition the combinational logic. Now, question is that how does one place the register, okay, judiciously in the data path? Judiciously meaning that we will place the register in such a way that it will reduce the delay of the maximum path, okay, I mean, of the maximum delay path, and also those register would be shared among the other computers. That we will see in the successive time. Okay. So that we have seen, right? That how to calculate T. So in the earlier, right? So whatever the source and destination pair we have, right? We have to find out the D, and then we have to decide the T. Now you see, we are taking the max, right? So what the max is telling us? So max is telling us that you partition the logic in such a way that each partition would take almost equal of time. Otherwise, what will happen? Like here you can see we are taking the maximum, right? The partition which dominates, meaning that it takes longest amount of time, that will decide the clock period. Okay. So in that way, we are saying that you should partition the logic, okay, the combination logic, in such a way that each partition would take same amount of time, so that T would be balanced. Okay. So that is what we discussed. Yeah. Now, so the principle here we discussed. So this is the a general principle to design the multi-cycle based processes. Okay, general principle. Okay, got it. So general principle is nothing but to first find out the dominating path or most delay path or maximum delay path, and then you chop that delay, okay, or partition that combination logic into smaller part, and you insert the register. Okay, that we'll see. Okay, so this is the general principle. Now we'll apply this principle into the MIPS processing. Okay, so here, so first as we have seen already that single cycle data path, right? So it has some problem. So single cycle design works well, but this is not the efficient one. Why? Because as we discussed, that clock period depends on the slowest instruction that we have in the ISA, right? That is here in this case LW1, right? And each instruction is taking the same amount of time that LW is taking. Okay. So this is not the balanced one, right? Because unnecessarily other instructions are waiting to finish its execution, right? Got it. And here the CPI is 1. Okay. And also, if you remember the data path, we have additional adder, right? And also we have two memories, one memory for instruction and other memory for data, right? So now we have to design, right, the data path in such a way that each instruction will take exact amount of time to finish its execution. Okay, so that is the secondary goal. Okay, so now we'll see. So here, what we'll do, we'll split the entire execution instruction execution cycle into smaller steps. Okay, so when we discuss the von Neumann model, if you remember, we have the 5 stages, right? So fetch, right, decode, right, and then execute, right, then memory, right, and then write back. Got it. So entire instruction execution has been uh, divided into smaller steps, and let's say these are the steps. Okay, got it. And here in this case, simple instruction will take right, exact amount of time to finish this execution. Okay, and the complex instruction will take a longer amount of time to finish this execution. Right, got it. And here, so I mean, if we want to design the multi-cycle processor, then same way we can design same way in the sense that so we follow the same principle that we follow when we design the single cycle processor. Okay, so what we have to do, we have to connect the architectural element, right, with the, like, so if you remember, architectural element is nothing but our register file, right, our memory, right? Okay, so we have connected them, right? And here what we have to do, we have to connect the architectural element with the storage element, okay, using the combination logic. So that we'll see. Okay, first we have to build the data path, and then we have to design the control. Okay, so in this case, right, here the what is the difference? What is the difference to design the controller? So controller will generate the control signals in a stepwise fashion. So earlier case, if you remember, for single cycle one, controller generates all the control signals at the very beginning of the execution of that instruction, right? So here, but here in this case, the multi-cycle one, it will generate the control signal stepwise. Okay, so that we will see. And here, so that controller would be designed using the finite state machine. Okay. So here, and also, I mean, the goal here is to minimize the resources, right? Resource utilization, right? So here we'll have only one memory, and meaning that, so that memory will share by the instruction and the data. Okay, so we'll keep the instruction and data in the same memory, and we'll remove the redundant adder. So we'll see. Okay, and then we have to incorporate the this register that we have discussed, right? So that we are saying here as a non-architectural element. Okay, and also these elements are not visible to the programmer, meaning that there is no instruction in the ISA for accessing this non-architectural element. That we'll see. Okay, now you can see these adders, right? These two adders are redundant, so we want to remove them. Also, you see we have the two memory here. Okay, so we want to combine these two memory into one memory, and that one memory would be shared by instruction as well as the data. Okay, and this data path, you can see this is for the single cycle data path. Okay, so we want to remove this adder. Now question is that if we remove this adder, right, who will perform such operation, right? Someone has to do that, and that time, so we'll share this operation, or ALU will perform such to addition. So ALU's load would increase. Okay, so that we will see. Okay, that we will remove this adder and the memory. Okay, so where do we place this operation that we have discussed? So ALU will perform such operation. And how does one control such operation? Using the marks. Okay, that we will see. Okay, so here in the data path we have the functional unit such as ALU. Okay. So and that would be shared. Right? And then we have only one memory, right? And memory would be shared by for the instruction will be shared by the instruction as well as data. And then we have the interconnection between the different component, right? And we'll design the balanced data path. Okay. So that we'll see balanced data path, meaning that each instruction will take exact amount of time to finish its execution. So that we'll see. Okay. So now, okay, so we want to fetch the instruction, right? If you remember, to fetch the instruction, what we have to do first, right? We have to draw the PC, right? Because PC holds the address, okay, and then we have the memory. So this is the one memory that we have. Let's say M. Okay. So what we have to do first? We have to bring the precise content into the memory address. Let's say M8. Got it? And so here the instruction would be available. Okay. And remember, we have to also increment the PC with 4, right? And that here in this case will perform it using the ALU. Okay. So this is ALU and we'll provide 4 here. Okay. And if you remember, ALU has ALU decoder. Okay. So this is our ALU decoder. Okay, we have to provide the ALU off field input, and controller will provide this ALU off. Then it will perform the addition, and then we load that result in the PC. Got it? Okay, sorry. Wait. So this is for instruction. Now we want to perform the PC's content, right? So we have to bring the. Got it? Now PC plus 4 is available here, right? Now we have this signal called PC write, meaning that so PC plus 4 is available here, right? Right. If we on this pin, right, then this enable input, then PC plus 4 would be written when there would be a clock. Got it? Now you see here we have fetch the instruction. So instruction is available here. Got it? Right? And we also perform the PC plus 4 using ALU. Right? Right? So let's say that is the T0 state. So during the T0 state, what we are doing? We are fetching the instruction, right? And then we are also performing PC equals to PC plus 4. Okay. Now we have fetched the instruction. Someone has to hold that, right? Otherwise, right, we have to generate the control signals, right? Now let's say we have here the additional register called, say, IR register, instruction register. Okay, it will hold the instruction. And to hold that instruction, okay, we also have here like the enable input. Okay, so that is, let's say, called IR write. Right, meaning that if we make it 1, then only that instruction will come from this point to this register. Okay, and also we have clock. Okay, so this is the phase stage, and you see here, so this is the non-architectural element. This IR is nothing but non element, meaning that this register cannot be accessed, okay, via the by the program. Okay, because we don't have any instruction in the ISA to access this register. Okay, these are the non-architectural elements. Got it? What are the architectural elements? Architectural elements such as memory, right, register file, and we have the instruction in the ISA to access memory as well as the register file. Got it? So this is the distinction. So non-architectural elements are not accessible by the program or to the program. Right? Got it? So that we have seen, right? We have inserted one non-architectural element, right? Now, so we want to draw the data path for LW instruction. Right? So what are the steps? Like if you remember for LW, so first we have to fetch the instruction, and then we have to calculate the effective address, right? So we'll do such a thing in a stepwise manner. So first we will fetch the instruction. Okay, and for that, this is the step. You can see first we are loading the instruction in the IR. Okay, and at the same time we are incrementing the PC by 4, and then you can see we are reading the value from the register file. That we are doing in the second step, right? And then we are holding that one in the other non-architectural elements such as A. Okay, so let us first complete these 2 steps. Then we will discuss the third step. Okay, and fourth and fifth step. Okay, so to fetch the instruction, what we have to do? We have to bring the PC's content, right, into the memory element. Right? So we have data memory, we have the memory M. Okay, so we have here memory address. Then we have the non-architectural element. If you remember, we just saw this is IR, and it has a enable input or IR write. Got it? So we'll hold the instruction here. Got it? Now what we have to do? We have to read the data, right, to calculate the effective address, and data is available in the register file. So now, so let's say this is register A. Okay. So we'll provide, register address A. So to calculate the effective address, we need the RS field from this. So RS field is coming here, and the width of this RS field is nothing but 5 bit. And here in the register file, we have 32 number of register. So we have to identify one. So then the data would be, corresponding data would be available here. And now we are storing that data in the other non-architectural element. And here, let's say that is A register. Okay. So data would be available here. Right. Now we have to perform the addition, right, to calculate the effective address. Then we need LUE here. Got it? Okay. Okay. Now we have to give the offset also here, right? And here before offset is, in our case, offset is 16-bit, right? And we have to extend it. Okay. So let's say we have the sign extension unit. Okay. So we have to provide the offset. Let's say we take the offset, right? So that is, if you remember, 15 to 0 or offset. Okay. And then it would be extended for 32-bit, and then we'll give it to the A. So this is our ALU. Now, right, ALU performs several operations. Then we have to choose one operation, and for that purpose we have ALU decoder. Okay. So we have to provide ALU off, and controller will provide this ALU off. Okay. And this ALU decoder also takes the, remember, the fun field, right? And we have to provide the fun field from here. Okay, so right. Okay, and then so we'll get the effective address here, right? Okay, address is available, right? Now we have to provide that address here, right? Now you see, so we have only one address in the memory. So what we have to do? We need, right? Because this address code is getting the value from two different sources. One source is PC and other source is ALU, right? So now before that, what we have to do? We have to store that address, okay, in another register. Let's say that is the ALU out. We will store the address here, got it? And we'll provide that address from this ALU out to the memory, right? Memory address. So what we have to do? We have to provide multiplexer here, right? You have to remember, because this one is getting, right? So one source would be your PC, and another source would be this ALU out. Got it? Now here, right? So this would be 0, and let's say, so this is, and here, so we have to I or D. It will take whether the address is for instruction or for the data. So here in this case, for here, this one is for data, because we have to read the data now, right? So now the address is available here now. So the data would be available via this output, right? Now we have to say whether it is data or instruction. If it is data, then we'll store this one in the other register, let's say MDR, or memory data register, MDR. Okay, so that data would be available. Got it, right? Now that data would be available here also, but this IR write, IR write, what we have to do? We have to provide the address from this ALU out to the memory, right? So what we have to do? We have to provide this IR write that time would be 0, right? And the data would be available here. We'll load the data in the MDR. And then after the next time, right? If you remember here, you can see the steps, right? Here we have computed the address, right? And the address is available in the ALU out, and we are giving that address to the memory, and then data is available in the MDR. Now what we have to do in the next step, we have to write the data back to the register. So here this is the right address, right data, right? Is the right data. Now we have to provide the register right address, and that will come from the higher field, higher address. So let's say that part will take, and that is the right address. And then what we have to do, we have to say register right. Got it. We make it 1, then the data would be right, and clock would come here in the passage of the clock. Got it. So data will be right here. Got it. So this is the LW's data path. Okay. Now we'll see the other instance data path, that is the SW. Got it. So first what we have to do, we have to, so what are the step here? First, in the first step, we'll fetch the instruction and we'll load into the higher register. And in the next step, what we'll do, we'll read the value into the that non-architectural element that we saw A, and then we have another non-architectural element such as B here. So we are reading. If you remember, so register file can read 2 data at a time. However, it can write only 1 data at a time, right? So, and then in the third step, what we are doing, we are performing the address calculation, right? So store means it will read the value from the register file, and then it will write such that data into the data memory, right? And you can see that we are reading that data from B register to the memory. Okay, so let's see. So, right, so first what we have the PC, right? And first we have to bring the PC's content into the memory address, right? Now here we are directly connecting. What we will see, we need marks here. We will see. Okay, then the instruction would be available here. Then we'll load that instruction in the IR register, and during that time, here we have IR write signal. We have to enable during the fetch time. Okay, so its data will be available here, or the instruction will be available here, and then we have to read the, so that we see, you can see, right? So this is happening in the first step, right? And then, right, we have to increment the PC also by 4, right? So that we'll do using the ALU, right? So that we have discussed, let's say, during the phase time, right? So that we just discussed here, right? That is happening, right? So here, right? So we have also ALU. Through ALU, we'll perform the PC plus 4, right? So let's say if we want to perform that also. So here. So this is coming. Now you see we have to provide 4. So we provide 4 first, and then the data would go here. Okay. That will happen in the first step. You see, we are not storing that PC plus 4 any in between. It's directly going back to the PC. Got it. And we'll provide the corresponding signal through ALU decoder, and we provide the ALU mod. Right. Okay. So data will be right here, the PC plus 4. Now, in the next step, we'll perform this operation. We'll read the corresponding data in the. So here we have, let's say, A register. Okay, so we provide RS here. Okay, so RS field. So data would be available here. And then also we provide the RT. Okay. So that will write in the other register B. Okay. And then now you see we have to calculate the effective address. And for calculating the effective address, we need A data and the offset. Right. So let's say an offset is here 5-bit. Sorry, 16 bit. So offset is 16 bit. We have to extend it. Okay. So we'll take that 16 bit and we'll provide it here. Okay. And here we'll get the 32 bit. Now we have to provide that one into the ALU because this is our ALU. Now you see ALU's hand, right? This lower hand, right? It already, it got the value 4 when we were calculating the PC plus 4. Now what do we have to do? Because this hand will get the data from the 2 different sources. So we have to, right? We have to provide marks here. Got it. So it, so we have marks here. So one input to this marks would be this one, and other input will be this one. Okay, and let's say the select input. Okay, so that let's say ALU SRCB. Okay, so ALU source SRCB. Got it. And now, so we have to provide the B. Sorry, we have to provide the A to the ALU. Because see, through this we are providing the offset. Right? Now see, we have to the A is available here. Right? Now we need another marks to the right. So we have to we need one more marks here. Okay. So output here. Now this is one input. Another one would be this one. Got it. And so select input of these marks. Let's say that is A L U A. Okay. Now we have to mention the as it is marked, so we have to tell the 0 and 1, right? So here, let's say when this is 0, then we'll take the PC value. If it is 1, we'll take the A value. Similarly, for here, let's say if it is okay, so 0, the same way like here, let's say if this is 1, then we'll take PC, sorry 4, and if it is 0, then we'll take sign extension. Okay. Now we have to provide the corresponding value of, then it will perform the calculation, right? That is the effective address. Now we'll store the address in the ALU. This is ALU output. Okay, so address would stored here. Okay, however, PC value, PC plus 4, you can say we are not storing in the ALU out. So we are storing the address here. Got it? So what we have to do now, this address, right? We have to provide in the memory. Now you see here memory, right? This address code will get the value from two different sources. So what circuitry do we need here? Mux or multiplexer, right? So we have to provide mux here. Got it. So mux 0 1. Okay. And if you remember, so this one would be I or D instruction or data selected. So if it is if it is PC, then it would be instruction, and if it is ALU out, then it would be your address bar date. Now address is available. Okay. Address is available. Now we have to provide the data. Data. So data is available here in the B. Right? So let's say this is memory data. So we have to bring the data on B. Got it. And then we have to say memory. Alright. Then data would be right here. Okay. Okay. So now we'll see the data path for archetype instance. Okay. So same way, first we have what we have to do. We have to read the instruction and we'll load it in the IR register, and then at the same time we'll perform PC+4 through ALU, and then we'll read two values because archetype means here you can say add instruction, right? So you will perform addition of R1, R2 and R3, and we'll store that one in the R1 register, right? Got it. And so what we have to do, let's say we have here data memory. We have here, let's say, register file. And we have ALU here. And we have marks. Okay. Connected. So PC is available here. Okay. This is PC, right? We have also marks we have seen for earlier example, right? So here this is I or D. This is memory address. Then here we have, remember, IR register. So first we'll bring the PC's content to the memory address register. I mean, we have to provide the address, and then we'll read the instruction here. Instruction will be available in the IR register, and we have to enable the right this, remember. So this is IR, right? Got it. Then right, we have to provide the two value, that RS and active here, and data would available in A and B. Okay. And before that, like if you remember, we have to perform PC+4. Okay, so for that purpose, we have to bring the PC to bring the PC from this point. And we have another, this is A. And this is A, is C, A. And we have value, this is C, B. And here we have 0, 1. Now we have B here. So So we'll provide RS. Let's say this is register address A, register address B. Then two value would be available in A register and B register. Okay, right. So second step is done. Now we have to perform the addition. So we have to connect B. So okay. So if you remember in the earlier case, so we are providing 4 to 1 and S and sign extension using 0, right? Then B we have to provide the B using other connection, right? Maybe we can provide B using, let's say, 2. This max time is going to increase, right? Okay. So here we will have 2 bit. And then you have to provide ALU decoder. So you have to provide ALU off and also the, remember, the fun field, right? And that will come via this higher register. This is fun field. Then so the result would be available in the ALU out. So this is ALU out. Now what you have to do? You have to write the result into the R1 register. So what we have to do? You have to write this one, right? Back. So let's say we need data, register, write data, and then write address. Write address would provide from the this higher and then the address and the value would come by this, and then to say okay, yep. That's it. So this is the data path for add or archive instance. Okay. So we'll stop here today.